Hello, welcome to Flare Builder online workshop session 7, where we will talk about Flare systems, protocol, and the related infrastructure. I am Alen Orvanic. I'm head of developers at Flare. I'm involved in development of different protocols, but today we will talk about Flare system protocol. We will have questions and answers at the end. What is Flare systems protocol? We can describe it as a bonding tissue for all Flare data protocols. And it kind of makes all data protocols enshrined. This is a strange notion, enshrined, and what does it actually mean? It means kind of tightly integrated with L1, so level of validation. So usually we have like validation, and then protocols are developed on the level of smart contracts. Sometimes they have different validators and different things how they are getting managed. But enshrined in our case means that we kind of join the roles of validators and data providers, which are participants in data protocols, kind of validators for data. We join them in the same role. With this, we ensure that we have the same security as on L1. So on the validation level, on blockchain level, we achieve the same security also with data protocols. Also, with this approach, we can integrate protocols, data protocols, a little bit better. So we can kind of make some code in smart contracts and then kind of prioritize some code, do some tweaks that kind of prioritize our protocols, which is not possible on other blockchains just through smart contracts. Like on Ethereum, you would need to convince Ethereum developers to tweak a little bit your code on validator level. In Flare, we can afford this because we are developing integrated blockchain and data protocols. So that's the meaning of enshrined. So let's see where and what is this Flare systems protocol. You are probably aware from previous workshops that we have several data protocols. Among them, one is Flare Time Series Oracle, or FTSO, and Flare Data Connector, FDC. But these two protocols are actually based on some set of pieces of models within infrastructure, which supports these two protocols. Yeah? And these pieces of infrastructure, we jointly call it with kind of umbrella name, Flare Systems Protocol. And today we will see what are these pieces and what's their role and how they support protocols like FDC and FTSO. And in the future, we already announced our Flare 2.0 vision. We are planning to integrate another protocol, which is called Protocol Managed Wallet, which will, beside those existing data protocols that help bring data from external world to our chain in a secure way, Protocol Managed Wallet actually enables us to steer the actions on all other external chains. So we can get data and we can execute actions on other chains. But now let's go back to Flare Systems Protocol. We have our Flare blockchain, which is smart contract blockchain and a platform for development of different dApps. And then there is this layer of called Flare System Protocol, where we have certain functionalities. One set of functionality supports signing of certain things. So when you are working in blockchain environment, blockchains, you have validator nodes. These nodes agree on blocks, and they show their agreement by signing certain things with their digital signature. And when you have enough of these signatures, you can digitally cryptographically check that, okay, most of them agree, so we accept that. In Flare data protocols, we are also having this kind of problem, challenge, that let's say data providers are bringing certain data on chain, and then they have to agree on that. Let's say on FDC, they have to agree on attestation response. And this is indicated by assigning by data providers of certain messages and certain data. And Flare Systems Protocol enables us or provides the infrastructure that enables those signing, which actually means definition, who are the signers, what's their power in signing and voting, and then counting these votes and reaching consensus and these kind of things. So signing is very important thing. The next module is scheduling. You may know that we are distributing rewards every 3.5 days through so-called reward epochs, but then the FTSO and FDC, they works on shorter periods, 90-second periods of voting, and we need to organize this scheduling, what's happening when. So Flare Systems Protocol takes care of scheduling as well. Also, you know, these protocols, let's say FTSO, and data providers involved with them, they involve some messaging, meaning like data providers need to send some messages to some smart contracts on a blockchain, and this can be pretty expensive. So we have to figure out how to do this as cheap as possible in terms of gas usage. And Flare Systems Protocol enables us to achieve this goal quite well. Then we count under Flare Systems Protocol also level 1 validation, which is kind of already built in. Then another part is called finalization. Finalization is essentially a procedure when data providers sign some message and agree on something, and then somebody collects all those signatures and verification that we have enough of those signatures, and then publishing the result. It's called finalization. But then all protocols need some incentives to run. Otherwise, data providers wouldn't participate, or incentives also includes like penalizations or encouragements, or maybe they would not participate in a non-malicious way. So we have in each protocol some custom rewarding, and Flare Systems Protocol takes care of some common infrastructure which enables rewarding and claiming rewards. So you can, if you participate in delegations and staking, you can kind of earn rewards as well. So Flare Systems Protocol is one layer of certain infrastructure that supports all other protocols. And as said, those protocols are then interfaces to the external world, either by being able to securely transfer data, like from internet APIs, exchanges, bank data, sports data, whatever that data providers can agree with some consensus. But with protocol managed wallet, we will also have execution capability on other chains based on what happens on Flare blockchain. So what are kind of main goals when we were designing this Flare Systems Protocol that we wanted to achieve? We know that on blockchains, except if you're Solana, storage and calculations are very expensive. So we wanted to have a system where we can kind of offload storage externally, and then maybe store on chain just very short proofs. Also, where we can do external calculations. Let's say each data provider does something, and then they just produce results, and then they put a proof on blockchain. So that we have kind of minimum calculation, minimum storage on blockchains, but still we can afford to use any data and any computation results. Yeah? Then the idea is, okay, if all this data is not stored on chain, how can we use it? And the thing is, like, we have this so-called data availability layer where data is replicated and stored. And for instance, with FDC, if you need to use some proof, let's say that some Bitcoin payment was executed with certain amount between two certain addresses, then you bring the data, you bring the proof, and then we have within FSP a mechanism where you can kind of prove, okay, this data that I brought, it's verified, so smart contracts can use. So that was the main goal why all that infrastructure was built, to leverage Flare blockchain, which is not so data intensive as, let's say, Solana, but to kind of achieve similar results. So let's go through those models in Flare Systems protocol and see how they assemble together and what are the main ideas. Yeah? First, we have these guys, data providers, which are, we said also they are validators. We sometimes call them just data providers or entities, but we think of them like, okay, these are some entities run by certain groups of people or people, and they run some clients for different data protocols, and they run also validator nodes. And there is a smart contract called Entity Manager on which a data provider registers itself, and registers also assigns certain addresses, and also registers which validator nodes are owned by a data provider. And then we have a system of how each data provider obtains the weight. And weight, it's important in voting and consensus. So like if you are participating, let's say in FTSO, then we are calculating weighted median, and according to the weight that data provider has, that's the influence on the weighted median. Or in FDC, we have those signatures, and we need some threshold, like 50% of all the weight of signatures has to sign something to be approved. And so at this point, it's important to know how that weight is accrued by each data provider. And of course, one source of getting weight are stakes on the validator nodes, the ones that are assigned to data provider. So this is done by staking on P-chain, but then we have within FSP a system which is called P-chain weight mirroring, which kind of copies each stake to some smart contract, so that the counting of weight is there in smart contracts on C-chain, so smart contract chain. Yeah? And data provider, as you probably know, it can get weight also from another source. These are the delegations. So you can delegate to data providers. And then the joint weight for voting, for signing things, is calculated like approximately like using this formula. We have delegations, and they are capped to 2.5% of total possible wrapped flares, plus all the mirrored stake from nodes, with exponent 0.75. That's kind of strange formula, but that exponent kind of ensures that if some data provider is getting weight too quickly, then this formula kind of smooths a little bit. Yeah? That's the weight of a data provider. We can call it also signing weight. But on the other hand, each address can participate that weight. Yeah? And as we said, through delegation, if you delegate 100 flare, first you need to wrap it and then delegate. Then you assigned a weight of 100 flare to one data provider, delegation weight. If you stake like 50,000 flare, which is the minimum amount on one of the up to four validator nodes assigned to certain data providers, that stake gets mirrored and then assigned to a data provider. So now we have some basis. So data providers, they have weight. We know how they can get it through community participation, staking delegations. So now let's look into the scheduling part of FSP. So we have something called voting epoch, which is essentially a frequency of data provider voting. So for example, FTSO scaling or anchor prices reaches consensus every 90 seconds through some kind of voting by data providers. So data providers, they send their prices, and then median is calculated, and this sending, and then some additional details. But then this happens every 90 seconds. And that's a step for voting in the protocols. Yeah. And then we have like each voting epoch is enumerated. Yeah? We start counting from some first initial epoch when we started Flare. But then you have like sequence of those. And then if we group like 3,360 of them, yeah? So this is, if you divide 3.5 days with 90, you would get this number. These are called, so that period of 3.5 days is called reward epoch. And why do we use this reward epoch? These are periods for reward calculation and then distribution. That's one aspect of that. So when a reward epoch passes, we have some code that indexes all the data, reads all the data about last 3.5 days, and then calculates according to rules who gets what part of reward. We will address this a little bit later. And then we kind of propose rewards, and then data providers agree or no. Usually they do on that. So that's reward distribution. You can imagine that each of these protocols has different tweaks based on behavior of data providers when they get reward or not, or where they get penalized if they do something possibly malicious and so on. So this is a period for reward distribution. Data is collected after it's passed and calculations carried out off-chain. And that's quite a complicated calculation because a lot of data and a lot of details. On the other hand, we use reward epochs for a period in which signing policy is fixed. What is signing policy? It's actually, we'll see a little bit later, a definition: who are data providers, what's their weight, and what's the threshold that they need to achieve when voting on something, or signing, so that the thing gets approved, like prices in FTSO. Okay, but then how are these votes or these data or those messages efficiently stored somewhere so everybody can read and nobody would miss any message? Yeah? So that's why FSP takes care of on-chain messaging. So here we have like one voting round enumerated as 0. And then we have another enumerated by 1, but we have certain periods because, you know, we have like this 90 seconds is a period of repetition. But then if you carry out some voting, you maybe have certain steps. For instance, in FTSO, you have commit first, then reveal, and then you calculate something called Merkle tree, and then you sign it and submit. So there are like 3 steps in FTSO. In FDC, you have bit voting is one step, and one is signing. Yeah? So you can see that in certain parts, at certain timestamps or around those timestamps, some messages need to be deposited on chain. And chain is used as some resource that every data provider can read, and they can see the same view on data. So, for example, if you know on a blockchain that you have a sequence of blocks from some timestamp to another timestamp, start and timestamp, and then one block more, then you can be pretty sure that everybody, not pretty sure, like 100% almost sure, that if you see those blocks between these two timestamps, everybody sees the same, so everybody sees exactly the same transactions and messages and everything. So it's kind of, we use blockchain to have a common view on whole process of voting. Yeah, and then we have like few predetermined functions which we use for sending messages. Actually, these functions are on smart contract called submission. That smart contract is special because here that enshrinement comes in place. It's special because it's some tweak on validator node is done so that these transactions are cheaper for data providers. So data providers, if they use submit one function call on submission contract, one call per 90 seconds, it's subsidized. That means that they can say, oh, I'm giving gas price very big, like enormous, but when transaction is executed, actually it's not charged that fee, but it's charged some minimal fee. But the effect is that data providers can, with one submit two, and one submit signatures, get prioritized when packing in blocks, because prioritization takes place based on how much fee you give. Yeah? So that's one important part of enshrinement. But in summary, data providers who are in some signing policy, so they are selected for voting in one voting round, they have a right to send prioritized transactions on chain. And that's important part of FSP. So like this would be one voting sequence, then one skewed, one voting epoch more. So you notice that we call the period window of voting epoch, but the sequence of these messages, which extends to 2 rounds, it's called voting round. So that's why everything is happening in 90 seconds. Yeah. So as I said, we have in this way prioritized transactions. How do we achieve cheap storage? We don't store data into smart contracts, which is expensive, but we just keep it in function parameters, so-called call data, and that's like 20 times more cheaper. Yeah. Also, these messages are reused between protocols. So for instance, submit to is used both for FTSO reveal and bit voting in FDC. And as I mentioned, with all of that, we achieve availability. So everybody can be sure that between two timestamps has all data. So data providers can then query blocks, get all the data, and then if, let's say for median calculations, if everybody has exactly the same algorithm to process this data and calculate median, everybody will get the same median. So that's very important. Otherwise, how can they agree on certain data? Okay, now let's get back to signing policy. I already described what the signing policy is. It's very simple. It's we choose before the start of one reward epoch, we choose who are data providers, what are their weights, and then what's the threshold for consensus, meaning like it's always like 50% plus of weight. And signing policy is used, so signatures, yeah. So whatever voting is done in any protocol, the data providers bring some messages, yeah. And then you can imagine like in real life, you have some document on a paper, and then when you when you collect enough signatures, that document is approved. That's essentially what's happening within our protocols. And then when you have enough signatures, you can publish this in smart contract, and smart contracts can check that there is enough signature. And only thing that needs to be done, or we need to be aware of, is who can be signer and what's their importance. Wait. Okay, but then how this signing policy is created before every reward epoch. So we have like here a diagram, a timeline where we have a start of reward epoch 0, and there is some signing policy there. And then as the end of that reward epoch is approaching, new signing policy for the next one needs to be established. And here we will see the procedure how this happens. So like 2 hours before the end of the reward epoch 0, there is some also enshrined mechanism. There's one special smart contract called Flare Daemon, which is kind of timer for our protocols. And it's special for Flare. And like 2 hours before the end of the reward epoch, some process is triggered, which is called vote power block selection. So Flare, as you are doing delegations and mirroring, Flare contract for wrapped Flare keeps track to what's the weight of each account. So that's the vote power. What's at each block. And then if we choose a random block, let's say past in current reward epoch, like in last 3.5 days, then if we choose this randomly, then we kind of ensure that somebody could not manipulate and accrue a lot of weight for a very short period, and then have big weight and then have big vote power. So because nobody knows that's random up to that point, nobody can prepare for that. So the only reasonable strategy is that you try to accrue as much weight through delegation stakes, encourage community to delegate, you behave well, and so on, give good fees. That's why we use randomness. So we have this vote power block, and that block, the weights in that block determine the weights for everybody, also data providers. But now data providers come in. We call this then next 30-minute period voter registration. So data providers have now time to call certain functions on voter registry smart contract and register themselves with the weight. And that's a competitive permissionless registration with 100 spots. And like if 100 spots are filled, then if some candidate for data provider comes in and it has higher weight than somebody on the list, it kicks out the one with smallest weight. And that's how we get up to 100 data providers with the highest vote power, so weight. Yeah. Then after that 30 minutes, a snapshot of signing policy is obtained, also using this timer built in Flare smart contracts and validator, and it's pushed to some special contract called relay. That contract needs to be aware of signing policies, and the relay contract is essentially a contract to which you bring some result, signatures, and that contract counts the signatures, weights, and if the weight goes over threshold, it publishes the result there. So you have the results there, but they are not like data results, they are like proof results, very short proofs called Merkle trees. Yeah? So that happens 1.5 hours usually before the end of the reward epoch, but that signing policy is for the next reward epoch 1. Yeah? And then we do another thing, we kind of force data providers in the reward epoch 0, so the ones that are currently active, to sign new signing policy. So kind of they agree with it. If they don't sign that, so you notice that the process is done in smart contracts, the definition of signing policy is automatic, but we still want to force data providers to sign it. And that's very useful because once we have signing policy, we can relay it on other blockchains. That's why this relay smart contract has the name relay, because if you have that smart contract on other chains, it just counts the signatures on other chains and publishes result. That's the essence of relaying in all blockchains. So consensus signing, sometimes they have like bridges which have multi-sig, but we have here like threshold consensus signing with signing policy. Yeah? So that's very useful, both for relaying on other chains and in future now, as we are building this protocol managed wallet, to relaying signing policies to TE wallet machines. So now I will show you one complicated diagram thing, how this voting happens. So you might get lost in that, but I hope you will just get the feeling what's happening here. Yeah? So let's say we have one protocol, like let's say FTSO, and it has ID 100. And then we are voting in some voting round, let's say 7,000, which happens to be in reward epoch 1. And how I want to show you how data providers are involved and how these pieces of FSP come together. So we have a data provider, let's say one, yeah, and then we have a Flare blockchain. And as said, we use submit one, submit two, those messages on the submission contract for cheap and reliable message storage. And what data providers do, they are sending messages through those functions, and these messages are encoded in the function parameter data. So message could be, these are my prices, or these are my must prices, or this is my signature, this kind of messages. And you can imagine that all data providers do that. But now let's focus on one data provider. Yeah? That data provider has then some algorithm there, depending on a protocol. Yeah? And what it does is, after certain block gets mined, after certain timestamp, it collects all messages. For instance, in FTSO, you collect all commits, which end up to certain timestamp, all reveals, and then you compare them if prices are okay, and then you calculate medians. And with all those assurances that I mentioned around messages, and with everybody running the same calculation algorithm, everybody should get the same medians. Yeah? So these are results. So you can imagine these are like 50 medians for 50 different price feeds. But then we don't want to store all those 50 or maybe in future 100,000 prices on chain, because it's expensive. We want to store on chain just some compressed thing, which is very short. And here we use Merkle trees. Merkle tree is some cryptographic primitive, which sounds sophisticated, but it's actually a method where you can take many pieces of data, and then from all of those data, you can calculate one number. It's a big number, like maybe 30, 40 digits, but it's still a small number, just one number, compared to data in terms of bytes that can be in megabytes, whatever. And then that Merkle tree has Merkle root, so it's one hash. And we create one message. We say this Merkle root is one number. Here is encoded with this pink number. It belongs to voting round 7,000 for protocol that. And then data provider with signature in the signing policies, which is approved for that reward epoch, signs the message and sends it on blockchain. And all data providers do the same. But then also it stores all the results and this message and Merkle tree, how it's to some service called data availability service, and or layer we call it also. And here are the data, but on chain we will store only one proof. And then with data and little more pieces of additional data, one can prove that that data was a result of calculation algorithm, and you can use it as a valid price. So that gets signed and sent on blockchain. But then somebody, that can be any user, we call it finalizer, can say, oh, I'm monitoring those signatures. Oh, I can collect now enough of them and send it to that vote counting contract, which is called relay contract. So essentially, from blockchain, it collects signatures, at least 50% of weight, doesn't need more. Then you collect signing policy, it's on some smart contract, and then you take from that message, sometimes from chain. In FDC, you actually have to take it from data availability service, because we just deposit signature. On FTSO, we also deposit message, pack this together, send this to relay smart contract, and that procedure, bringing all signatures for a message, it's called finalization. And relay smart contract checks signatures against the signing policy, and if it sees that it has enough signature, it publishes, it says, for protocol 100, let's say FTSO, in voting round 7,000, the result is this. And only this small number is on the relay contract. Also, relay contract here, it's aware of signing policies. So that's a procedure that keeps repeating in FDC, FTSO scaling, FTSO fast up. It's a little bit different, though it uses signing policies for selecting who can adopt price. But this procedure will also be used in instead of having Flare blockchain here with TEs, trusted execution environment machines for protocol managed wallet. So now I will just show you how a user can use data, let's say prices for FTSO scaling. You can take it from a data availability service. So you find the Merkle tree in which this is it, the actual price, and then there is associated with this Merkle trees some additional small data that you have to bring with it, which is called Merkle proof. So user that wants to use it collects those pieces of data from availability service. So the data, actual data or result, and that additional pieces, which is called Merkle proof. And then some smart contract, let's say some loaning contract, and you want to perform some liquidation, needs to prove that price has changed, and the user brings this data, calls certain functions, let's say liquidate something, and the contract says, okay, you brought some data. I don't know if I believe it, but I'll check if it's valid. And then it makes a hash of data and then applies this Merkle proofs. It also involves some hashing something. And then if everything is okay, the end result must match this number 0x1234. And that smart contract just checks on the relay contract, was this number approved? Yeah, it was. And then it says, cool, now I believe to user that that data is valid and belongs to that voting round. It's fresh enough because voting round 700 was previous one. So I can act on that data. So that's how relay contract works. Now let's quickly go through reward calculation. So it's kind of last model. So as I mentioned, these protocols are running. You can see data providers are constantly sending some messages. Maybe some malicious data providers are sending wrong messages, so on and so on. But then reward epoch sends, and we have all those messages on chain. And then we have a script which is public. Any person can use it, even data providers. Collect all the data from chain for us 3.5 days, run that script, and you get the distribution of rewards. And the result of that script is a list of so-called reward claims. And what is a claim? It's simply who gets what amount of reward. Yeah? This address gets this amount. That address gets that amount. Yeah? And then what we do is take that list of claims and again use that similar procedure like Merkle tree. So instead of proofs of results putting for FTSOs prices, putting them into this structured Merkle tree, we make a Merkle tree. So we collect together all the claims, so who gets what, and then calculate one little proof, which is called Merkle root. And then data providers, after the end of reward epoch, need to vote. So by signing on a Flare Systems Manager smart contract, need to vote confirming the Merkle root. By that, they confirm that they agree with all the claims and whole off-chain calculation. And I can tell you that off-chain calculation is quite consuming. It takes like a few minutes to calculate, depending on implementation. Some implementations we have like even longer. So, and then by just approving Merkle root for all claims, we are ready to pay out rewards. There is a smart contract called Reward Manager. And once the Merkle root is approved, any user can bring, similar like before, the previous 2 slides ago, you bring from data availability layer the claim. So I can get this much amount of Flare. Yeah? And Merkle proof, so this is some short few pieces of data additionally. I can bring it to the claim function reward manager, and I get money. But then there is, because we don't want to have millions of claims for all delegations, we aggregate them together. And consequently, delegators and stakers do not need to worry about claiming, because we make one aggregate claim that is assigned to a data provider. Let's say one claim that says all delegators who get 200,000 Flare, and then that data provider, we have one system, brings that claim and initializes distribution between delegators. So consequently, delegators can just, once this is done, just call, give me the reward, and you get delegation reward, or give me the reward for my staking on certain node ID. And that's how things work. So why is FSP important? You can see that actually it enables all existing protocols. It takes care that it's kind of well integrated, prioritized, works well, yeah, and secure in the context. And what it enables us is it kind of defines both the signing weights and signing policies for data providers, and takes care of rewarding. And actually, similar like it enabled the development of FDC and FTSO2 protocol, it will be used, the same signing policy, it will be used on protocol managed wallet. So essentially, you can think of, if you have looked into the block about Flare 2.0 vision, you can see that if data providers agree with their signatures in the signing policies more than threshold, then something will happen in TE machine, which basically with protocol managed wallet means that protocol managed wallet holds private key for some other blockchain, let's say Bitcoin, and it can trigger payment on the other wallet. But actually, it turns out that we can, with infrastructure based on protocol managed wallet, we can also provide next versions of FDC and FTSO. FDC takes like 3 to 4 minutes for confirmation. With this new infrastructure based around protocol managed wallet, we'll have FDC that essentially in matter of seconds you get attestations. And we are also envisaged some trusted and confidential compute with TEs. So protocol managed wallet are some specialties, but we want to kind of extend computation outside smart contracts or outside joint data provider calculations like medians to direct TEs. So that's more or less it. So here are the QR codes for our socials, and if you have questions. No questions. I wouldn't dare to say everything is clear. If you have any question, please shoot it. So no. Otherwise, we have a quiz. You can use this QR code to access online quiz, and you get a chance to win some Flare merch. Well, have a nice day.